Hello everyone, welcome to second lecture of the course, AutoGIS. So from this week on, things get even more exciting. I know I've been saying that for 2 months, but believe me, this time we're really starting to do some GIS. So for many of you, this has been the major motivation. So from today on, we are actually doing something like proper GIS. So yeah, so this is exciting in that way. And yeah, there were a couple of questions about how to do exercises and everything. There were not so many, but most of you have continued from first period, and last period we had a whole lecture on this thing. So we covered GitHub and like how to do things. So for some of you who have joined just from this period, no wonder it might be a bit confusing. So we have the Friday sessions for that purpose, specific, not for many reasons, for any question you have, but it's a good time to ask those questions because, as I said, in last period we spent like 1 or 2 lectures talking about those things, and we simply don't have time to cover those again. So if you have still problems with submissions and exercises, then Friday sessions are the place to ask those questions. So yeah, so as I said, today we are going to work with GIS in Python, and finally we are going to meet GeoPandas, the library that you have heard about a few times, well, many times, but today we actually start working with it. As you can guess from the name, GeoPandas is a library building on top of pandas, so everything you have learned in the first period you are going to need now. So you will probably find yourself visiting the GeoPython course website many times. If you don't remember how to group things or select with pandas, then you are going to need it. So those who have studied GeoPython, they know where to find things. Those of you who have not taken GeoPython course, then you might need to visit that website more often. Yeah, so we are going to use GeoPandas today. It combines the power of pandas to analyze tabular data and Shapely and handling geometries and many other things that we will learn about. So today we are going to learn how to read and write spatial data from and to files, and how to manipulate geometries and how to transform between different coordinate systems. So one of the key things in world of GIS when working with data is handling the coordinate system, projection, and that's something we are going to learn today, and it's quite easy with GeoPandas. So the learning goals for today: reading and writing spatial data from different formats, filter and regrouping data by spatial and non-spatial characteristics, and managing and transforming between different coordinate systems. So that's the agenda for today. Do you have any comments, questions from last week? How was the first exercise? How did the auto-grading behave? Did it work fine? Especially from the first 2 exercises, the auto-grading system is a bit, we have had it for a few years, so probably it works better. From exercise 3, it's new, so that's when the bugs will appear probably. But hopefully it will work fine and will support you in completing the exercises. But yeah, let's get started. I already pulled the lessons. So you should have lesson 2 folder here. We are working with 4 different notebook files, so we have more contents to cover. But before getting to the notebook, let's quickly go through some key concepts that we will be working with. As I said last week, we are not going to really teach GIS, but rather see how to do GIS with Python. But to make sure we remember what we are talking about, let's quickly go through these terms that we will need today. So do we all know what a shapefile is? Just raise your hand if you don't know. Okay, so we all know what shapefile is. Shapefile is a vector data format that was started by Esri. Many people hate shapefile, but it's super common, so that's why we still continue working with it. Yeah, so we will see how it works. A shapefile, the name suggests that it's just one file, but in reality it's a bunch of files. So when you get your shapefile, you will end up with a bunch of files with different extensions. So the main one holding the geometries is the .shp file, but you also have like .prj, keeping information about the projection, .dbf, the database file holding information about the tabular data. So we will work with shapefile today. Then we have GeoPackage. Have you used GeoPackage before? Yeah, so GeoPackage is also a file format. It's more complex and it's more favored nowadays because it's open source. It's not tied to any company. And it's very powerful, so it's not a single file. You can work with raster. You can store raster in GeoPackage. You can store vector data. You can also, like if you have those of you who are used to ArcGIS, you know probably geodatabases. So it's a, you can think of it as a database, as a directory where you can hold different layers of data. So it's more than just a single data format. So we will also work with GeoPackage today. Coordinate systems, I'm sure you know what they are. Datum, also linked to coordinate system, is the surface, the model for Earth that is used in the coordinate system. And EPSG, do you remember what that is? Yeah, so it's the short code. It's a short code system for coordinate systems. So it's European Petroleum something. So it started for a certain specific organization, but then it was very common because you know the names for coordinates, there are thousands of them, there are many of them, and the names are long. So it's become a habit by many people to just use this 4-digit EPSG code to refer to a coordinate system. So there's some more explanation and some useful links if you want to learn about any of these concepts, but let's get started with coding. So the first thing we are covering is managing file paths. So it's not specifically GIS related, but we are going to use this in every lesson. It's a good habit to have. So let's quickly go through that. Okay, so has it happened to any of you that you write a piece of code on Noppe or on one of your computers, and then you take it to another computer and you run into issue with the file path? Just raise your hand. I won't ask further questions. Just raise your hand if you have had the experience. Yeah, so to some of you. This is especially a problem if you change between different operating systems. So if you have written a piece of code, like for me, it happens because I personally use a Windows, and you can see Noppe is running on Linux. So if I was not managing the file path properly, then we would have had problem during this course. So it's a good habit to handle your file path systematically in a way that is transferable between different computers and different operating systems. So a good habit that we already saw in the last period was to use relative path. So if you're just keeping your files next to your notebook, it's a better habit to have a relative path to it. So instead of giving the full path starting from your drive exactly to the file, you just give the path relative to where your notebook file is. So if your notebook file is here and you have your data under the data directory, so I don't care what drive it is on. It's just from where I am, it's in data, then the file. So it's relative to where I am. So that's a good habit, but that doesn't always solve the problems. One of the problems we have, especially when working with different operating systems, is that these different operating systems handle file paths differently. One of the most obvious differences is between these slashes. So for example, Unix-based machines like Linux or Mac OS use the forward slashes, and Microsoft Windows uses backslashes. So if you have written your code with backslashes and it works fine on Windows, you might go to a Unix-based machine and get into trouble. So that's why we are going to learn tricks how to make your code bulletproof from that aspect at least. So yeah, so it used to be a source of problem because Python didn't handle this very well in older versions. And then there was a library called OS Path that allowed you to handle directories rather well, but still, it worked fine if you moved from one Windows machine to another Windows or from one Unix machine to another one. But if you were moving from Windows to Unix or vice versa, then it didn't handle it so well unless you specifically foresaw the situation. But now there is a library available already from version 3.4, and it's inbuilt, so you don't have to install it separately. And it handles things very easily and smoothly. And the name of the library is pathlib. So let's start by importing the library, and we will see how it works. So I import the library, and then the next thing you do is to create a pathlib object. So you initiate the pathlib object, and that is easy to do. So you just write pathlib.path with P capital. So this initiates the path, so it sees where you are working from. So it knows that, okay, this notebook, where you're working from. In our case, we are working with a notebook. It knows where you are. Yeah, so if you were running this on Windows, for example, this would have said Windows path. But it doesn't matter because we are doing this using this library and handles things for us. So let's do this again, but this time I'm storing this object that I'm creating in a variable, so I can work with it. So I will store it under a variable called path. So I will use this pathlib.path again. So the output is stored there. If you want to translate this object into a real path that you can read, like where it is exactly located, then you have to resolve it. And this is how you would resolve it. So I will resolve it and store it in the same variable. So using path.resolve, you can get the actual path to the file. And to show you what the output is, I will just put the variable name here so we can see it on the screen. And this is where we are located in our work environment. And the path looks weird, and the reason is that we are on Noppe. So this is where we are located on Noppe, and then this is my folder. So my work folder, then I've created well, this is where I am essentially. So by resolving the path, you can see where you actually are. Yeah, so this will be different if you're running this on different machines, and probably in your case it's different if you have named your folders differently. So there are a bunch of things you can do with this library. There are a lot of things you can check the documentations, but some of the most useful ones. If you want to check if a path exists, and that can be useful if you're automating a process and you want to make sure a folder exists when you want to export the file, then you can just use path.exists, and it will return a Boolean value. So in this case, our folder exists. That's where we are. Lesson 2 exists. If it was a wrong path or something that doesn't exist, then you would have gotten false as the output. If you want to check if the path is to actually a file or a directory or a folder, then you can check path.is there. So is it a directory or not? In this case it is, because we are working with lesson 2, this one, and it's a folder. It's not a file. So if at the end of the path you would add, I don't know, geopandas.ipymb, then it would become a file. This would return false. But now it's telling you that it's a path. So a bunch of other things that we are not going to try here, but just to let you know that you can do these things. So if you want to rename a path or a file, you can just use path.rename and give a new name to it. If you want to delete a file, you use path.unlink. And if you want to remove a directory, then you use path.removeDirectory, RMDIR. So we are not going to delete anything here, but just to let you know that this is possible. Okay, so what we will be doing every week in every exercise, in every lesson, is that we create the object for path, we resolve it, and then from there it's easy to give path to whatever file we need. So now remember, we have resolved our path. The next thing I'm going to do is to tell Python where my data is actually located. So I'm going to create a new variable called data directory. So this is how you can manage paths. So we already know what path is, where we are located. If you want to navigate to a folder, you can just do it easily, like this. So I want to go inside directory called data, which is right next to my folder. And you always go with this / regardless of what operating system you're using. So path/data. So to see what we are getting as the output, I will just write the name of the variable here. So now you can see we navigated to the data folder. So if you want to go one folder back, then you can use .parent, so it goes one folder back. So if now you're in data, but you want to go back to lesson 2, then you just write path.parent, but we did it on path. So path was where we are now, it's lesson 2. We went one folder back to notebooks. So you can repeat this several times if you want to go many folders back, or you can just create a new directory path. Okay, so this is what we will be doing every week with every lesson. So we import the pathlib library. We resolve the path, so we know where we are. And from there we create but we often have a data folder, like in this case. So we create this data directory variable where we say, okay, this is where my data is stored. So let's run this. So now we want to quickly try this. We are going to revisit topic of GeoPandas and importing data, but to just quickly show you how this works. Once you have defined your path, then I'm going to import GeoPandas. And from GeoPandas, you can read the file. And this is how I'm providing the path. So I already know where my data directory is. And if there are still other folders in my data directory, you can just add a /, the name of folder, until you get to the name of the file. So this is how we will be managing our path in this second period. And it's a good habit. So you can continue what we have done in the first period, but this is a safer way of handling file path. So in this case, we are loading the data and creating a quick plot. So let's run the cell. And we quickly created a map of Finland from this Finland municipalities GeoPackage that we have under our data folder. So we are going to get back to this shortly, but you can see that you can create maps fairly easily. Of course, we learn how to create details, but the same matplotlib method that we used in the first period works with geospatial data as well. So you just put .plot, it plots your data. So one thing is that here I have used name capital. I've written the name of the variable in capital, and that's a good coding practice. In some programming languages, you can define a variable that is constant. Like in C languages, you can define a constant, meaning that you cannot update it. So you define, I know, the pi value, 3.14, and define it as a constant. You cannot update it anymore. In Python, we don't have this concept, so we don't have constants. You just have regular variables, and you can always update them. But to make things like to show the user that this is something that you don't want to change in the code, you write the name in capital. So it's a habit. So this is whoever, like when we were writing this code, we are telling the user that, okay, data directory is data directory. Don't change that unless you really have to. So if you see the name of a variable is written in capital, there is a good chance that the coder is telling you that this is a constant, so don't don't change it. But in practice, it's not a constant, so you can still update it. It's just a good coding practice because Python doesn't have a way of handling, well, constant variables. Okay, so this was a quick introduction into pathlib, and we are going to use this all the time, so you will get very used to it. But essentially, what you're going to see every time is these 3 lines of code. So we start with this, and that's all we need for now. Is it clear? Yeah. Okay, so now let's get started with vector data. So I will open the next notebook file, vector data. Okay, we are all familiar with vector data, and we know how it's different from raster. And it depends on what kind of GIS work you do, but at least in my work, what I've used mostly is vector data, so it's more common. But again, it depends on who you ask. If you're working a lot with, for example, satellite imagery, then you're very used to working with raster files. But anyway, there's a very big diversity when it comes to vector data that you can get your hands on and use for your analysis. As I mentioned, one of the most common file formats is shapefile. Still, a lot of data sets you get from different sources come in shapefile format, even if it's not, like at least the GIS people don't like it so much because it's tied to a company and also it's a bit tricky. For example, the fact that it comes as a bunch of files makes it a bit difficult to send it to people. So you see, if you want to send a shapefile to someone, you have to zip the folder and send it. So it's a bit like tricky. So I have mentioned already the GDAL library, which is a huge GIS, geospatial science library under Python. So a lot of things that you do are provided by GDAL. So it's a backbone of many things that happen in QGIS, backbone of many things that happen in even ArcGIS. So a lot of things that we are also using in GeoPandas is coming from GDAL, even if we don't acknowledge it. So there's a library that handles the file imports and exports. It's called Fiona. So Fiona is very powerful when it comes to importing and exporting geospatial data files. For vector data, for raster data, we will see later, we will work with a library called Rasterio for importing and exporting and also doing some analysis. So Fiona gives you very low-level access to files. So if you really want to do low-level changes to things, then you can directly access Fiona. But Fiona is included in GeoPandas. So if your job is to just import the files, you don't need to use Fiona explicitly. You can just use GeoPandas to import the file or export the file. And just remember that GeoPandas is actually using Fiona. So that's the library that allows us to handle files in GeoPandas. So let's get it started by doing this. So we are creating the path, what we just learned 5 minutes ago. So we have a bunch of data files stored in the data folder. So I start by defining the data directory. So I want to get from Fiona. So Fiona is very powerful. And one of the great things about Fiona is that it can handle many different file formats. Okay. Okay, let's quickly install Fiona. So remember, whenever you are missing a library, for example, when you're doing your final assignment, you might want to use other libraries. So you can just directly install it from here, like this. Yeah, so from Fiona, I'm getting Fiona supported drivers. And here you get a bunch of different file extensions, file formats that can be read and written by Fiona. So there are some letters appearing. So these are the file formats, so DXF, CSV, and we have the Esri JSON, we have Esri shapefile, GeoJSON, like many formats that you're familiar with. GPX is what you usually get from GPS devices, and map info. So Fiona can read and write a DXF file. And A is short for appending. So with different formats, it has different capabilities. So with some of them, it can just read. With some of them, it can read and write. With some of them, it can also append. So it can alter the data contents as well. So the files that we will be working with a lot, GeoPackage, you can read, write, append. So it has full functionality when it comes to GeoPackage. For example, you see with GPS files, it can only read and write. It cannot alter the data, which is often not a problem. You just import it, you do whatever calculation you want, then you can export it to another GPX file or another format. And same with shapefiles. So also with shapefiles, you have full functionalities. You can read and write and alter or append to the data. Yeah, so with Fiona, you can handle almost any file format that you may come across in your GIS fork. Okay, so let's start working with GeoPandas and see how we can import data. So the first thing I'm going to do is to import my library, GeoPandas. I'm going to go with full name because that's how we have done it in this course, to just remain consistent. But it's a common habit to import GeoPandas as GPD. So many people do that. So if you end up doing this, just remember to stay consistent or remember how you have done it. I will go with the full name. And I'm going to import a data set of municipalities in Finland. And I'm going to store it under a variable called municipalities. And this is how you would import data in GeoPandas. So very similar to what we have done previously with pandas. One thing here is that you don't have to specify which file format it is. It's just read file. So in pandas, we have to specify. So geopandas.read file, and then the next thing you do is to provide the path to your file. So remember that we have already defined the data directory. So that's nice. You don't have to do anything. But the data is actually under some subfolder that is called Finland_municipalities. And the file name is Finland municipalities, so Finland_municipalities_2021. And remember to also add the extension of the file, which is a GPKG. And as I said, GeoPandas is essentially working on pandas, so you can use the same methods there. So once I import my data, I want to look at the head of my data. And remember, you can easily do that using the name of the variable where you're storing your data, .head. I'm sure I've typed municipalities wrong somewhere, but hopefully not. Okay, I didn't type it wrong. So yeah, the data was imported. And you can see that it looks fine. So you have your different columns. So you have the name in Swedish, you have the name in Finnish, you have some code. And there are a bunch of other columns with information about each municipality. And one column you can see here is geometry. And that's where things happen. So this is essentially what makes, so this is a geodata frame. Remember in the first period we were working with data frames, data series. So in GIS version of pandas, which is GeoPandas, we are dealing with geodata frames and geoseries. And the difference is that geometry column. So everything else is the same. You have the columns, they're tabular data. What makes this different is that you have a column called geometry, and that holds the geometries. And probably you can guess already, the format is probably familiar for you from last week. So it's coming from Shapely. So that's why it looks the same as what we saw last week. So we are dealing essentially with tuples of coordinates that are handled by Shapely. So this is what makes our data different from last period when we were just working with pandas. Yeah, so this is how you import your data using GeoPandas. There's another feature, but there are many features, many details how you can import things. But one good thing coming with GeoPandas is that you can import directly from a zip file. So as I said, one of the problems with shapefiles is that they often come in zip format because they're not one file. Like in this case, we have a data. We are not even downloading it like explicitly at least. So I know that this file goes to a zip file containing some shape files, and I can just directly read the file from the zip. So you don't have to extract it and then just work with it. So if that's the situation, you have a path, a URL to a zip file containing shape files, or if it's on your own computer, of course you can extract them, work with it, but if not, you can also just work with the zip file as it is. So this is another example of a format that you may come across. So GeoJSON is also a common format, especially in the internet. So we have also a data set called Europe Nuts Regions.GeoJSON, and importing it is exactly the same. So like I said, with GeoPandas, doesn't matter. It's the same function you use for importing. So it's read file. You just give the path to the file and the name of the file which contains the extension. So in this case, it's a GeoJSON, and it works fine. Okay, so we learned how to import data files, very simple, geopandas.read file. Saving files is also quite simple. So remember, we just imported some data here from a GeoJSON, nuts_region. So let's export this to another format. Let's export it to a file. So this is how you would export files. So I will just write nuts region, which is where I'm storing my data. And in order to save your file, you just write to_file. The next thing you need to do is to provide a path. Where do you want to save the file? I want to save it under my data directory. So the same folder as where I'm keeping everything else. And of course, you have to provide a name for your file and the extension. So I'm going to save it as Europe nuts_regions. And here is where you specify what format you want to use. I'm going to save it as a GeoJSON, but you can just save it as a shapefile or other formats similarly. So you can see a file was created here 4 seconds ago in my case. So it's the same file you exported here. So it's very similar to how you import files. Very easy. We are not going to work with databases in this course, but just remember that this also works very nicely. GeoPandas works very nicely with databases as well. So some of you might have experience. If you have more experience with Python, you might have heard about the library called SQL Alchemy. So if you want to stay in Python and do database work, there's a very good library called SQL Alchemy that handles a lot of the SQL operations. So if you end up using that, remember that you can just connect to your database, and GeoPanda can actually handle that. So you can just read your data from the database. So you don't have to export it to other formats. So in this case, we are not going to use it, but if you end up using with PostGIS, for example, then you can just import the data directly to GeoPandas. Another thing you can do with GeoPandas is importing data straightly from WFS, or World Feature Service. So this is a service that many of you might have seen already in your other courses or other work. So many organizations share their vector data using WFS. So you can just import your data using GeoPandas straightly from WFS. So we are not going to go through how this is constructed. You have seen this probably before. In WFS, there is usually information, so you will see how to construct this. And for many of us, a good starting point is QGIS, actually, to see exactly what is in the WFS. And from there, you can just come back here and import your data. So this works. So yesterday I tried this, it was working. Today there was some gateway 502 error. So it's coming from Helsinki map services. So if the service is down, and this happens very often with WFS, that service is down. So if you get error, there is a good chance that there is something wrong with their service. I remember last year we were getting some SSL error, some certificate error, so we had to add some exception to be able to import the data. But they have resolved the issue, apparently. Yeah, so we just imported the data directly from WFS, and with the right coordinate system, we are going to deal with this later today. And you can specify, well, this is WFS, you can specify the bounding box where from you want to get data. And there it is. So now you have it here as a geo data frame, and you can continue doing your GIS work. And similarly, you can see it's the geodata frame. You have a geometry column here. Yeah, so that was importing data with GeoPandas. Very easy. Just one line of code. Importing, exporting. You can work with different formats, different sources of data. And that's it. So was it easy enough importing and exporting GIS data? Yeah, so now that we know how to handle data in GeoPandas, let's get to know about GeoPandas a bit. So I opened a new notebook file called GeoPandas and Introduction. Yeah, so like I mentioned, it's very similar to Pandas, but also it has some capabilities coming from a bunch of other libraries. For example, it works with Shapely for geometries. It works with PipeRoach for, it's another Python library that handles coordinate systems. It has Fiona, you saw, it uses Fiona for importing files, a bunch of other things. And a key difference that I already mentioned is the data format in GeoPandas. So in GeoPandas, you're working with geodata frames and geoseries. Remember, data frame is two-dimensional. This is a table. You have rows and columns. A Pandas series, a data series, is one-dimensional. So it's either one column of your data or just one row. In this case, if you have a geometry column, if your series is basically a geometry column, or if you have a table and you have the geometry column, then it automatically becomes a geodata frame because it looks for the column name geometry. We will see later how we can rename that or do other things, or assign it manually. But it automatically looks for a column called geometry, and then if it's there, it will be recognized as a geodata frame. So that's the main difference. Otherwise, most things work in a similar way. Okay, so let's import some data and take a look at it. Yeah, so this is what I was telling you about. We are importing some data from some topographic database. We are going to work with this a bit more later on today. But what I'm trying to show you here is that what we already saw. So we have a geometry column. In this case, it's polygon, Shapely polygon, and this is a vector data with polygons. Yeah, and of course you will have probably other columns, other tabular data that will appear there as well. So this is appearing red because we did some formatting here to show you. This is the geometry column, but yeah. So now we are going to do some work. We are using some data, the Finnish topographic database. The data has been downloaded before from Python and it's already there, so we don't have to download any data. But yeah, so there's some information about the data. It's provided by National Land Survey of Finland, and it's open data, so it's free to use. It comes with a bunch of metadata. It has very detailed metadata, so if you want to learn more about what the data entails and how it's been collected and everything, then you can just check out the source. It also comes with a separate Excel sheet that tells you what each of the columns mean. So you know, very often in GIS data the column names are short, so if you're not sure what they mean because they're too short, or if they're in a language you don't understand, then there's a separate Excel file linked here that you can check to see what the columns mean. And this is where the data comes from. You're familiar with this service, Python. So we have downloaded data, and it's somewhere in the data folder here. So now we are going to work with our data, starting with defining the file path. So I will run this cell. Everything is already typed in. So in this lesson, we will focus on the terrain objects. So we will work with different feature groups. So as you can see in this data set, there's a column with name of the feature. So we have different kinds of terrain. So there can be fields, gardens, meadows, cemetery. So there are different kinds of classes. And we are interested in certain kind of classes, and we want to export them to separate files. So that's what we are going to try to do. And while we are doing that, we will practice a few things in GeoPandas. So I've already checked the metadata for the data set that we got from National Land Survey, and I know that the data that we are looking for, or what we are interested in, starts with M in the name and ends with P. That's by National Land Survey's convention. So the data that we are interested in starts with M, ends with P. So something like this. So in this case, it's a shapefile starting with M, ending with P. And there are different codes referring to different tiles. So the data is from a large area, from whole Finland. Then there are different files for different tiles, referring to different areas around the country. So these tiles. So I want to find the file. So there are a bunch of files in that folder. So it's under Finland Topographic Database. Let's go check it out. It's under Data, Finland Topographic Database. So there are a bunch of files here, and it's shapefiles, so it has made it even more messy because there's so many files. So if you want to import the right file, of course you can just find the file from here, give the exact name, and import it. But because we want to also practice something, we take a different approach. So first, let's define our path to this folder. So topographic database. So we already defined data directory, but this data we are interested in is under this other folder. So let's just run this cell. So this is very similar to what we did in first period. Remember the globe function for looking for certain files with certain names. So a similar property exists also with this pathlib library that we are working with. So I'm going to create a list of all the files that start with M, end with P, because I'm looking for one file and I'm lazy to type in the exact name, or in this case we want to just practice. So I give the path to the file. I will just copy this because it's a long name. So in this folder, use the globe function, similar to what we did in the first period, but now we are doing it with a different library. Find me all the files that start with M, after the M, it can be anything. So there are many tiles, and it can be anything. So I can get all the tiles. but I want it to end with P. So it starts with M. It can be anything in between, then P. And the extension of the file is SHP. It's a shapefile. So in this case, it's just one file. We could have just typed in the name. But like I said, I want to show you how the globe method works. So what it does, it returns an iterator, the globe. But to make our life easy, since we are comfortable working with lists, I just converted it to a list. And this is the output I get. So you can see it's a Python list, starting and ending with a square bracket. And what we have inside is the path to the file. So in this case, we only have one file that starts with M and ends with P. But imagine if you wanted to automate the process and you had a bunch of files that have similar name. Then you could have gotten a list of them and you could automate this. And we did something similar to this in the first period. Okay, so now I have the file path here, input file name. Well, we converted it to a list. Now we are just loading the first item in the list. But in this case, we only have one item, but anyway, index 0. And I'm storing it under input file name. So now the path to that file that I'm interested in is defined, starting with M, ending with P. It's a shapefile. Okay, this was just accessing the file. The rest is the actual work. So I'm going to import GeoPandas. And I'm going to load my data and store it under a variable called data. And remember, you can easily import your data using geopandas.read_file. And we have already stored the name, the path to the file under input file name. Okay, now that the data is loaded, let's do one of the things we have tried many times before, and that's checking the type of the data. You can see that the data you just imported is a geodata frame. So it looks good. So I'm going to also look at the head of my data to see if the import was successful or if there's any problem with my data. It's data.head. And it looks fine. Similarly, you can look at data.tail, remember, if you wanted to look at the last 5 rows in your data. And I always check the geometry. But I already knew it would be there because it's been recognized as a geodata frame. And remember that with pandas, if you want to get a list of the columns you have in your data, you can just easily write data.columns. And it returns you a list of all the columns that are in the data. So again, as I said, if you're interested in this data, we are not really working with it so much here. But if you're interested, you can just check out what these columns mean. But we are interested in only a couple of the columns here. And these are the columns that actually we are interested in. So I'm going to make a selection of my data and store it under the same variable. So from data, I want to just keep a bunch of columns. So one of the columns that I want to keep is Ruhma, which has been written like this, meaning group. So the second the column I want to keep is the column that holds information about the class. So I will keep luokka. And remember, we are doing GIS here. So remember to also import your geometry. Otherwise, we will end up with a data frame and you cannot do GIS. So I'm going to import my geometry column as well. So let's just run this. Now we have made a selection from our data. Next thing I'm going to do is to rename my columns, because English is easier for many of us in this class. So I'm going to rename my column from Ryhmä to group and from luokka to class. So I will have English names. And we saw this already in the first period, and we have practiced this many times. We just define a dictionary with old name, new name, and then we use data.rename to rename the columns. So nothing new here. Let's confirm that the renaming was successful. So I'm going to look at the head of my data again. And it worked. So we have renamed the column names to English. Yeah, so as I said, this is pandas. So let's take 2 minutes and practice a few things that you learned from pandas. For example, get the number of rows you have in your data. Remember how you did that. Or get the number of unique classes you have in your data. So let's take a minute or two to just practice some of our pandas skills, and then we continue with exploring the data. Okay, so as you probably see, it works very similar to pandas. So everything you learned there is you're going to need here. Okay, another thing that you learned in the first period was visualizing your data. And like I said, pandas uses matplotlib for visualization. GeoPandas is using pandas. So again, here we are using matplotlib for visualization. So remember that if you just use data.plot on your data, like in the first period, we were working with other kinds of data, like the temperatures, you could create a chart. In this case, in GeoPandas, it knows that it's a geodata frame and it knows that there is a geometry column. So it automatically, when you use .plot on a geodata frame, it automatically creates a map for you. And that's great, because we are doing GIS here, and usually we are interested in visualizing our data. So before doing anything, we want to look at our data to see if it's the right data, if it is in the right coordinate system. Because here we are not in a software, so the data is not visible. So it's a good habit to plot your data frequently to see if everything is all right. So just use .plot. If you want to, we will see how to customize our visualizations. We will have a lecture, I guess, yeah, in a few weeks that you will specifically work with maps. But if you want to just quick visualization of your map, .plot gives you a map of the data. Yeah, so you might, if you're familiar with the area, you might recognize that this is data from Helsinki region, so you can see the shape. So yeah, so let's look a bit more closely at the geometry column in GeoPandas. So I'm going to access that column specifically, so data.geometry. and look at the head of that column, so the first 5 rows. And like I said before, this is familiar. It's in well-known text format. It's coming from Shapely, something that we worked with a lot last week. And the fact that it comes from Shapely means that everything we learned last week we can apply here. So for example, you learned how to get the area of a geometry. So you can do it here as well. So let's access, well, it's a data with many rows. I want to access only one geometry and visualize it the same way as we did last week. So I'm going to use something I learned from pandas. So I'm using @ method to look at my first row. And I want to specifically look at the geometry. So same as last week. So when you exactly point to that one geometry object, what you get is a Shapely object like last week. And what this essentially means is that you can just add a dot area here and get the area of that, for example. So every method we learned last week works here. So here is the example. I'm printing an F string, and I'm getting the area of my Shapely geometry. So remember, here you are getting the Shapely geometry. This is what we learned last week. This is how you get the area of your geometry, and I'm just rounding it. And that's it. So let's just run this. And you can see that this particular polygon is 76 square meters. And remember, last week I reminded you that, okay, when we were working with Shapely, we couldn't talk about meters, for example, because we didn't know about the units. But now this is real GIS data, and I know it's using a metric system. So now, if I get 76, I can safely say that this is square meters, because I know the coordinate system. But we are going to look at the coordinate system later. And this is, of course, pandas, GeoPandas, a geodata frame. So we learned in the first period how to iterate through the different rows of our geodata frame, or data frame as we referred to back then. So I'm making a loop here going through the first 5 rows of my data. So for index row, I go through the 5 first rows, and I'm calculating the area for each of them. So I get the geometry from each of them. Each row, from each row I get the geometry. I calculate the area, and I'm just printing it here. So I will just do it for 5 rows, not to fill the screen with prints. So you can access each of the geometries and print the output, as you can see here on the screen. Yeah, so if you need anything that we learned last week, any of those calculations, now you know how to access the geometry and then use those Shapely methods. So usually with your GIS calculation, you don't want to necessarily access one geometry in your data. You have a larger data set, for example, and you want to calculate the area for all your polygons. And let's see how we can do that. So if you just use data.area, it will calculate the area for each of the rows in your data. So in this case, we have 4,303 rows, and it's going to calculate the area for each of them. So in this case, I applied the area on a geodata frame. So it's data. Remember, data is the whole table. So it's 2-dimensional. It's a geodata frame. You can similarly do this on a data frame, the data series. So if you have just geometries, and I'm going to test that. So I will access only one column. And remember, when you have only one column, it's a series. Dot area. So I can do the same thing specifically on the geometry column. And I will get the same output. But what if you want to write it to a column? Well, do it first, then I will do it here. So let's take 30 seconds doing that. Do it on your own computer, then I do it here. So just create a new column called area and store this there. So you will end up with a new column with the area calculations. So doing it is easy, and we have done similar things last period, doing different kinds of calculations. So I just get the area and I store it under a new column called area, and I just put the name here so I can see the output. The good thing about Notebook Jupyter Lab is that the data is huge, but it doesn't show everything, so it just shows you the head and tail, which is nice. Yeah, so we calculated a new column called area, and it has the area calculations for each of the geometries, each row in my data. We will skip this part, but remember that in the first period we learned how to get descriptive statistics, for example, from data frames, so how to get the standard deviation, average, sum. So you can do the same thing here. So if you want to calculate the average area, you can just do that, or you can get the sum. So if you don't remember, you can just follow this link and see how it was done. But as I said many times already, everything you learned with pandas, you can apply here as well. Okay, so now we are interested in only, let's say we are interested in only one of the classes. And from the metadata, you can check what this refers to. Yeah, so I want to export only the lakes. So in my data, I have different land types, different kinds of terrains, but I want to only export lakes. And from the metadata, I know that the lakes were marked with this number. So if the class was 36200, it's a lake. So I'm making a selection from my data, only keeping the rows that have a value of 36200 for the class. And I know that number because I checked the metadata of the data. So there's no magic here, just read the documentation. And now if you want to plot the lakes, you can just write lakes.plot and easily create a visualization of the lakes that you have in this area. And then if you want to export specifically the lakes to a new file, so this is what you needed. You got a big data from National Land Survey, but what you were interested in was the data of the lakes in Helsinki area. So you just do a selection and then you export it as a new file. So this is how you do it. We saw already how to do it. So I'm exporting lakes to a file, giving the path, and this time I'm exporting as a shapefile. So just by changing the extension, the library knows what format you want. So I'm just exporting it as lakes.shp. Yeah, so you can export to many different formats as we saw before, but let's just export it as a shapefile. Yeah, and if you are curious, you can go to that folder and check the output. You will probably have a bunch of new files, .shp and .prj and dbf and so on. Yeah, so one thing that we learned in the first period, and we are going to redo it here now for our GIS data, is grouping. So remember, we did a grouping based on, what did we do the grouping based on last period? Yeah, it was based on dates. So we had some data in our, we were working with some temperature data, and we had some dates, and then we did the grouping. So now we want to do the grouping based on the terrain type. So the idea is the same. Now we are in GIS world, so we do something geographical. So we are doing that grouping now. So let's look at our data, just remember what we have. We have the geometry area, which we just calculated, and we have some group and class information. So I want to do the grouping based on the unique values in my classes. So based on the classes, so lakes, all lakes in one group, I don't know, all the meadows in the same group, and so on. So let's look at the unique values we have here, because of course there's repetition. There is not only one lake in Helsinki, there are many. So these are the unique values we have in our class column. And this is a reminder. So how did we create groups? So I'm going to create groups and store it under grouped data. And this is how you did the grouping in pandas. So exact same thing, data group by, and then you specify the column that you want to use for your grouping, and in this case we are using the class column for the grouping. And to see what I get as the output, I'm going to put the variable down here, group data. Yeah, so the grouping is done, and you remember that you end up with a pandas group by object, and then you can use that object to explore more. So I'm going to explore my grouped data more. I'm going to specifically look at the groups I have. And these are the groups. So yeah, so we have a lot of groups. So you remember that we can also simply iterate over the entire group by objects, and we can do something. For example, let's iterate over the groups and count how many rows of data we have in each of the groups. So from first period, remember, you just iterate for key, you write a for loop, you get the key for each group, the contents of the group, and then you use the len to count how many rows you have in each of the groups. And I'm just printing it here as a F string. Yeah, so you see we have many classes, and in each class you have a different number of rows. So some of them have only one, some of them have thousands, some of them have hundreds. So for example, lakes, what was the number for lakes? It was 36200. Yeah, so we have 56 lakes, for instance. And you probably remember that if you want to obtain a particular group, for example, in this case, lakes, you can just, from your group, you can get a particular group. So in this case, I know the lakes were 36200. So this is another way how I could have ended up with the lakes data. But of course, if you just wanted lakes, it's easier to make a selection. But if you want to make separate files, and that's what we are going to do, so we are going to export each terrain to a different shapefile, for example, then you do it with groups because it's more automatic. You don't have to do it manually. So now that we have these groups, we want to export each class to a different file. So everything is typed in, we just run the cell. So we are writing a for loop like we did just now. We iterate through the groups and we write them to a file. So this is the path, this is where I'm saving the file. One trick that I'm using here is here. So you're creating different files and you don't want to give them the same name for a number of reasons. First of all, if you're just making 100 files with the same name, you're overwriting them. So you don't want to do that. Even if it allows you to, you either get a warning that the file already exists, or it will just overwrite it. And the other thing is that it's useless. So if you're exporting lakes and then different kinds of land types, you probably want to give the right name to the data. So a useful trick is to use the F string. So remember that we have used countless times this f string to print something. You can also, well, f string edits, you can pass in a variable to a string with f string. So usually we have used it for printing something, but you can also use it for modifying the name of your file. So in every loop, I'm getting the key, which is the name of the class or the number for the class. And it's going to be added here to the name of the file. So each file will be named terrain underscore key. And the key here is the class type, the number, and then .shp. So this is a trick to modify the file names automatically, so you don't have to manually write, terrain underscore lakes.shp. So let's run this, and as you can see, it takes a while. It took like 5 seconds because we had 4,000 rows of data and a bunch of groups. But now we exported the data, so you can go check out, where was it? It was in here, I guess. Yeah, so we ended up with these files. This is how we named them. Terrain underscore key.shp. And it's a shape file, so you ended up with those other files as well. Yeah, so this is an example of handling your file. So these kind of things are very easy with Python. So imagine if you wanted to do this in QGIS or ArcGIS. It was a bit tricky. So programming, if you're working with, if you want to automate something, or if you're working with very large amounts of data, like in this case, it's easier. Yeah, so of course, you can export your data in whatever format you want. You can, for example, import it as a CSV. If you're calculating some statistics, you can just export it. So in whatever format you want. So here is an example. I'm going to calculate some statistics for the area column. So I'm getting the sum. So the sum of the areas for each class. So these are the values for each class, the sum of, so how much lake do I have in Helsinki, for instance. And then you want to export it maybe to a CSV, because in this case it's a statistics. You don't need to have it as a geodata frame. Then it's pandas. So you can just use area information dot to CSV. The simple pandas, you can export it to a CSV and you name it whatever you want. So if at any point you want to just export a data frame or CSV to just with a statistics or tabular data without geometry, then you can just export it the same way as you did in the first period. And that was it. Now you know how to work with GeoPandas. Do you have any questions from this part? Yeah, you already have the skills you need from first period to work with GeoPandas. So let's continue with one last thing for today, and that's coordinate systems. That's also very interesting for geographers and those working with GIS. So map projections. So we know that the coordinate system, coordinate reference system, is a crucial piece of metadata for each geospatial data that we work with. Otherwise, it's a bunch of numbers. So if we don't know how to map them, if we don't know what's the unit, then it's basically useless. And you get that information, of course, it usually comes with the file, if the file is correctly defined. So if you have a shape file and the shape file comes with the .prj file, the information is there. But sometimes it's missing, and then you get the information from the metadata. Yeah, so you already know about map projection, about coordinate system, and you know that very often we need to transform our data. So the data might come in a certain coordinate system. For example, you have gotten your data from Google OpenStreetMap, and it's coming in a Web Mercator. It's coming with, it's coming in WGS84, and then you are working in Finland, so you want to transform it to a coordinate system that works well in Finland. So we very often need to transform between layers. Another thing that we will see a lot during this course is that We have gotten a bit lazy with the software we work with. So if you are doing a special join in QGIS or ArcGIS, the chances are that the software handles the coordinate system for you. So if they are not in the same coordinate system, you don't get an error. It works. Because QGIS or ArcGIS is automatically handling the coordinate system for you. But in reality, they are in different worlds, so it shouldn't work. But when you're doing things in Python, then it doesn't work anymore. So if one of them is in a different coordinate system, the other one is another, and then you do a special join, they do not overlap because they're not in the same system. So that's why when working with Python particularly, you need to transform quite a lot, quite often. Yeah. Yeah, so here's some joke about projection systems. Yeah, so there's a bunch of useful links if you want to learn a bit more. You know that there's a lot of detail behind coordinate systems. There's a lot of math. So if you're curious, there are a lot of books out there and materials online. But let's get practical here and see how we can, in practice, handle coordinate system when we are working with Python and in GeoPandas. Yeah, so once you have figured out which projection system to use, and we have good practices, for example, we know in Finland what coordinate system to use, or so once you figure out what coordinate system you want to use, then the rest is easy. So there are libraries. There's a library in Python called PyProj that allows you to do a lot of projection related things, and it's in GeoPandas, so we don't need to explicitly access it. So you know that with Esri shapefile, you need a .prj file to have the information. So if this is missing, then you have to define it yourself. It won't be automatically recognized, the projection or coordinate system. But yeah, so let's start working with our data. So I will run this cell so the path to the files is defined. Next thing I'm going to do is import a data set from my EU countries. So it's the EU countries, European countries boundaries. It's a GeoPackage data. So if you're curious, you can already visualize your data. But I'm going to go straight to the coordinate system. So I'm going to access my EU countries, which I just imported. And the way to get CRS, it's very easy, .crs. That's all you need to type in to get the coordinate system information of your data. So I can see that the EPSG code for my coordinate system is 4326. It's the short code for it. It's WGS84. So it's coming from web. Like this is the format you would get if you're importing, for example, from OSM or Google Maps. Yeah, and a bunch of information. Yeah, what is the datum used, and some details about the coordinate system. Yeah, again, there are some links if you want to learn more about these standards, but I'm going to skip them and get to the next thing. So I'm going to access my geometries. And one way of this is a good practice for those of us who have worked with GIS a little bit more. By looking at the numbers, you already can guess what coordinate system it is from. Like, is it projected or not? Is it like longitude, latitude, or is it the X and Y? So it's a good practice to look at the geometry and see what you have. So in this case, it looks like longitude, latitude, and then So let's continue working with that. So let's assume that we want to project this. So we have gotten data from OSM and we want to continue analysis, and our data is from Finland, and we want to take it to 3035. And there's a link here, so if you want to learn more about this coordinate system. Yeah. So how do we project our data? that's also fairly easy. So I'm going to create a new variable, EU underscore countries underscore EPSG. So I'm just adding the name of the coordinate system so I know in what system I am. So this is the data I'm going to transform. So it was EU underscore countries. And this is how you do the transformation. So it's very easy, dot to CRS. And the easiest way with less chance of making a typo or a mistake is by providing the EPSG code for it. So if you just type in the EPSG code for your coordinate system, it's easier. There's less typing than putting the name. Yeah, so that's how you do the conversion or transformation. So let's look at the head of the data. And now you're in a projected system. So you can see by comparing the coordinates, you can see from this longitude and latitude, you ended up with this X and Y. So now you're in this projected coordinate system. Okay, now that we did the transformation, let's plot our data in both coordinate systems to see how it affects our visualization. So this is the exact same data. Now it's two different coordinate systems. So on the right, we have the WGS84. And then the right, we have the 3035 that we just transformed to. So again, it's not a surprise to any of us here that coordinate system affects the looks of your map. So for example, in the cartography course, we talk about this a lot, that you should be careful what coordinate system or what projection you're using. So yeah, so the projection was done, and this is what you ended up with. So now we are going to try, let's just export this as the output. So I'm exporting this as a GPKG file. So now we are handling different CRS formats. So yeah, before we get to different CRS formats, let's see how the projection is presented in this library. So remember, we are working with PyProach. Even if you are in GeoPandas, it's using PyProach. And PyProach has its own ways of representing coordinate systems. Yeah, so we are loading our CRS. So you can, it looks messy here, but you can have your coordinate system in different ways represented. So you can have it as a string, like this. You can have it in well-known text format, or you can have it in EPSG. So different ways of representing. So PyProach handles all these different ways. Like I said, it's easier to just transform and say, transform it to EPSG 3035, but you can also go with this other format. So you can go with this string. You can go with the well-known text format. And sometimes this is useful if you're using a coordinate system that has no EPSG. It's some custom-made or some very local projection you're using. Then you can provide it. And we will see an example of that later. Yeah, so there are different representations. If you want to get information about the coordinate system, probably you will just Google the coordinate system's name or the EPSG code and you get a lot of information. But imagine you're somewhere, you have no internet, just Python and PyProach. And PyProach can give you a bit of information. So if you are unsure how this coordinate system works, there is a bit of information here. So you can see what datum it's using and different details about it. What is the unit? So you can see it's coming in degrees. And from here, you can access certain things. So from CRS, I can get the name specifically. So the name of this coordinate system is WGS84. if you want to get the area of use, you know, there is some recommended area where the projection works well for. You can also get it from area of use.bounds. So it's a global coordinate system, so it works everywhere, or shouldn't be used everywhere, but in theory it works everywhere. So yeah, so you can get a bunch of information. So if you just put CRS, you get the whole thing, but if you specifically want to get the name, then from CRS you can access name or access the area of use. Yeah, so finally it's time to play around with some map projections. So for this we will use a global data set of country polygons that we have already saved in our data directory. It was downloaded from naturalearthdata.com, and now it's there, so we don't have to download it. And it's a good website for downloading for cartographers. So if you want different data to play with, this is one of the sources you can get some good data for your maps. So now we are going to load our data first, of course, and then we are going to visualize our data in different coordinate systems. So this is in WGS-84. This is the map we are used to. This is the coordinate system web maps use. So this is what is familiar for us, even if it's not very accurate. But yeah, WGS-84. Next time I'm going to use Web Mercator 3857. So let's visualize that. So this is how it looks like, and as you know, it works very badly with the North Pole and South Pole, and here it's not clipped, so you can see the South Pole becomes like this, because when you do the math and you're at -90, you end up with infinity, so that South Pole continues forever. So this is the same thing that is used, for example, in Google Maps, but it's clipped. But yeah, this is what you end up with. And then if you have some coordinate system that is not predefined, for example, if you want to use Eckert 4, you can also provide the details like this. So there's a structure you can use, but essentially you can use any coordinate system if it's not, if this might be a way you want to refer to it instead of EPSG, or if there's no EPSG code for it, you can just define it as a string. And in the documentation, you can see the structure of this. So it just tells you what is the projection used, and like what is the datum used, and so on. And the units. Yeah, so let's just run this. So this is our map in Eckert coordinate system. Yeah, and one last one, I guess is it Robinson? Oh. Yeah, so now we want to visualize our map in an orthographic projection. We can also get an orthographic map. So yeah, so there are a lot of projections to choose from, and we have seen examples a lot before. The point here is that you can easily work with coordinate systems in GeoPandas and transform between them very easily, just writing to CRS, and that's it. Yeah, and that was it for today. Our timing was very good. Do you have any questions? If not, that's it for today. You will have exercise 2. Everything is published already on the website. And you will be working with GeoPandas and projections this week. And see you next week. Well, actually, there is no class next week, so I will upload the video for you. But I will communicate with you on Discord. So, but see you in 2 weeks.